Hello, a great welcome to this series on PLAXIS. Myself, Jarajan P. PLAXIS is a finite element program used for the strength, deformation, and safety analysis. In geotechnical applications, in PLAXIS, PL stands for plastic and axis stands for axisymmetry. This is tutorial 1 in the series and it provides the bearing capacity analysis of a simple square footing. So let us first go to the problem statement. As you can see, the soil domain that is used in the present analysis is of 30 meter by 30 meter and the soil has a depth of 25 meter. Considering that the foundation size that is used in the analysis is 3 meter by 3 meter, we find that the soil domain extends approximately to a dimension of 10 times the foundation width, and that should be good enough. For the present analysis, we will not consider the entire domain. Considering that the soil as well as the foundation elements are symmetrical both about the horizontal and vertical axis, we will consider only 1/4 of the model dimension for the analysis. Accordingly, the model dimension will have a plan dimension of 15 meter by 15 meter. 15 meter is nothing but 30 by 2 and has a depth of 25 meter. The foundation size that is considered for the analysis will be 1.5 meter by 1.5 meter, which is 1/4 of this foundation size. Now, for the geotechnical analysis, we need to specify a proper material model, stiffness parameters, and the strength parameters. These are the minimum required parameters for the bearing capacity analysis. So for the present case, we shall use the Moore-Coulomb model for the plastic analysis. The drainage type considered will be the drained type. The unit weight both in the saturated and unsaturated conditions are considered as 2818 kN per meter cube. The stiffness parameters are specified in terms of the Young's modulus E, which is taken equal to 1.25 into 10 raised to 5 kN per meter square and a Poisson's ratio of 0.3. The strength parameters used for the analysis include the coefficient C value of 10 kN per meter square, a friction angle of phi equal to 35 degrees, and a dilatancy angle psi equal to 0 degrees. So let us start the PLAXIS program. So though this tutorial can be attempted using the 2D version, I have decided to choose the PLAXIS 3D for this tutorial. So when you open PLAXIS 3D, this is how the screen looks like, and here you have two options, either to start a new project or open an existing project. So start a new project. So here you will find that this is the screen for the PLAXIS 3D, and I just want to give you a very brief introduction of the various components available on the screen. So on the top you will find that there is the title bar, where you will be provided the name or the title of the file, and here right now we have not provided any title, so it is given as untitled, and you will also be provided an extension of the file. All the input files will have an extension of .p3d, and just below the title bar we have the menu bar that provides us the various operations required for completing the pre-processing stages of the model. And below this menu bar we have the toolbars, and the toolbar contains it performs almost the same operations as is also available under the menu bar. And below this toolbar we have the very important modes, that is the modes in the preprocessor. So we have, as you can see, 5 modes. First one is the soil. Obviously, as the name suggests, this mode is used to complete the soil stratigraphy descriptions, okay, provide all the properties of the soil, etc. And the structures, as the name suggests, it will help us to provide all the details regarding the plate elements, the beam elements, and also application of the prescribed displacements, boundary conditions, etc. And coming to the third one, that is the mesh. As the term indicates, it allows us to complete the meshing operation of the module, and it also has many additional facilities like to improve the local coarseness or the local fineness of the different parts of the model. And then we have got the water levels, and finally the stage reconstruction mode, and this is one of the very important mode of the PLAXIS pre-processing stage. And as you can see that the name indicates the staged. So PLAXIS has the facility or the capability to simulate the various construction stages involved in the problem or in the project. So accordingly, the engineers will be able to visualize the stress concentrations, the distribution of stresses and deformations as the construction progresses. This is one of the powerful features, and accordingly, we have to be very careful while defining the various stages involved in the construction. Right. So let us provide the project properties. But before that, I would like to take your attention to the left side of the screen. Here you will find that there are two areas. One is known as Model Explorer. Model Explorer is an area which is automatically populated by the PLAXIS as the model development is in progress. So here it will provide you the various details, like for example, the geometry, boreholes, and the loads, displacements, etc. Now just on the top of that, you will be able to see another one more area, that is a Selection Explorer. When you select an item in the Model Explorer, the corresponding details will be displayed in the Selection Explorer. So on the right side, you will find that there is a white drawing area where all the models will be displayed as the development is in progress. And just below this area, you will find that there is a command area also, where in addition to the GUI phase, that's a graphical user interface, you will also be able to develop the details of the model using the commands. Okay, the various details of the commands, their format, etc., are available in the reference manual of PLAXIS. So let us proceed for specifying the project properties. In the project properties, you find that there are two items. One is the project and the other one is the model. Here you will be able to specify the title of the project. So let us proceed. So I will just say is it tutorial 1, and I will say that it is the bearing capacity analysis, bearing capacity analysis. Okay, and I'll be able to provide some comments very specific to this project over this area, comments area, and you will also be able to add your company logo if any, because later on you will be able to take all these output files in the required format to your calculation report. So after the project, you can press the model, or you can use the next, press the next button. In the model area, you will find various items, like for example units. This units will provide you what are the default units that will be used for the tutorial or for the project. And for the current tutorial, we have chosen meter for the length and kilonewton for the force, and the day as a time unit. And as you can see that for the length, you have got various units like the inches, feet, millimeters, etc. And for the force also, you have got Newton, kilonewton, meganewton, kips, etc. Right? And on the right side, you will find that there's a general one which provides you the details regarding one constant, that is a gravity constant, and it is in the minus z direction. Remember that z is directed upward, and the earth gravity is given as 9.81 meter per second square. Now is a very important item, that's a contour. This contour defines the extents of the model or the contour limits of the model. As I have pointed out earlier, the model that will be used for this tutorial has a plan dimension of 15 meters by 15 meters. Though the actual soil domain is of 30 by 30, we are considering only 1/4 of it. So accordingly, I will put x minimum as 0 and x max, right? X max will provide us 15 meters. And similarly, my y minimum will be 0 and my y max will be 15. So we have rightly specified the plan dimensions of the model as 15 by 15 meters by specifying these contour limits. Okay. So once that is over, we can press OK. So please remember, right now we are in the soil mode. So we'll be able to specify all the soil stratigraphy, all the soil properties in this module. So now PLAXIS allows you to define the soil stratigraphy in many different ways. For this tutorial, what we'll do is that we'll make use of the borehole creating procedure for mentioning the soil stratigraphy. So just click this create borehole button. So once you create the borehole button, you will find that yes, you can place this borehole at some particular location. So here, as you can see that right now the coordinate is 0, 0, 0. So I am placing my borehole at this right at this origin. Okay, fine. So once you place this borehole, the menu applies. The new menu will appear that will ask you to modify the soil layers. So right now, as you know, the present tutorial has only one soil layer that has got a depth of 25 meters. So just add this. Okay. So now we know that okay, the top will be 0 and the bottom it is 25 meters. So the ground surface is z equal to 0. This means that the bottom of this soil layer will be at minus 25. Okay. So as you can see that yes, this 0 to 25. And here we can see that right now the water level it matches with the ground surface. So here there is one item known as head where you will be able to specify the position of this water table. In the present tutorial, we have decided to take the water table just at the bottom of this borehole. So this means that the head will be taken as a minus 25. Okay. So as you can see that yes, right now the water level or the water table has moved up to the bottom of the borehole. Now as you can see, we have rightly specified the extent of this borehole. In this way, we will be able to add many soil layers and we'll be able to specify the position of these soil layers in elevation. And this procedure is what we call as defining the soil stratigraphy. And right now here we can see that there is one important item known as material. So because once we define the various layers, next stage will be obviously definition or assignment of materials. Now this definition of this material can be done right at this location, that is by clicking the material, or you can go outside this menu. Okay, so let us just for the time being press OK. So as you can see that yes, right now the model is available over here, right? So let us visualize the full model. What you can do is that you can just press this reset zoom. So this is my 15 meters by 15 meters, right? And the depth is 25 meters, okay? And please note down very carefully the direction of X and Y axis is directed, for example, towards the right, Y axis, it is towards up, and Z is direct upwards, okay? And now, next, as I told, we need to define the material. So that can be directly done, show materials. So you just press this button. So you'll be able to define the various materials. Obviously, for this tutorial, we have only one soil layer, meaning that we have only one material to define. Now, as you can see that the PLAXIS, through this material sets, you'll be able to define the properties associated with the soil. You'll be able to define the uh, properties attached to the plates, geogrids, beams, embedded plates, angles, etc. So right now for this tutorial, you know that we need to define only one particular item, the properties, that is the soil. So we'll choose the soil and interfaces. Okay. So having done that, just press this new button. Okay. Now we'll be taken to a new menu that is soil. Okay, no name. So let's start defining. Here, as you can see that there are various items available: general parameters, flow parameters, interface, initial, etc. For some problems, maybe that you require hardly 2 or 3 of these levels. Okay, so let us start defining the properties. So identification name. So let us, for example, I want to rename it as sand. Okay, and you know that PLAXIS, just like any other geotechnical software, it has got a various constitutive laws that it defines what we call as the sustained behavior of the soil. So as you can see that here there are many models available, starting from the simple linear elastic Moore column, then we got a hardening and there's just small model. Many models are available for this. As for this, we want to select the simplest soil model available. That's a Moore column, and as rightly pointed out earlier, our water table is right at the bottom of the borehole. So accordingly, we would like to perform a drain analysis. You will also be able to perform a short-term undrained analysis as well, and you will be able to select a proper color for the identification of the material. As you can see that you can just change this color to some other. Okay, so you can just press anywhere along this color and select. So for this default color is chosen. And next you will find the general properties, that is gamma unsaturated. That means the unit weight of the soil when it is in the unsaturated condition, and then saturated when it is fully saturated. So for this project, we know that we have defined the unsaturated as 18 kilonewton per meter cube. Be very careful regarding the units, and saturated obviously 20 kilonewton per meter cube. So that's okay for us regarding the general. Now let's go the most important one, that's parameters. This section parameters will let you to define the important characteristics of the soil, like for example the stiffness that will govern the deformation, and next one is the strength that will provide what will be the capacity of the soil. So let us start with feeding the various one. For example, here we have got a E, that's the Young's modulus. The stiffness will be specified through the Young's modulus. Here, as you can see, that will be having a stiffness value of 125. Okay, right? 125 E3, 125 E3, right? So remember the unit for this Young's modulus will be kilometer per meter square. Okay, and the new value will be defining it as a say 0.30. Okay, so the new value, please remember the new value, that's a Poisson's ratio, and the stiffness values are to be correctly indicated because these are the critical parameters that will govern the deformation behavior of the soil. And remember here, once you enter these values of E and nu, the program automatically calculates the corresponding G value, that's the shear modulus. Also the E oido, that's the oidometer modulus. Okay, obviously we know that we have got a clear-cut expressions correlating E dash with the G and also with the E oidometer, that's the oidometer modulus. For example, you know that the G is calculated as E divided by 2 into 1 plus nu, where nu is the Poisson's ratio. And so these are the two main parameters, E dash and nu dash, that is required for the stiffness characterization. Next, let us proceed for the so-called strength parameters. For this problem tutorial, we have used a cohesion value of a ton, and we'll use a friction angle of 35 and the dilatancy angle. Okay, that will be chosen as 0. And we will not be using any kind of the flow parameters for this problem, or we don't have any kind of a soil structure interaction exercise, so this is also not important to us. So this means that we have completed the definition of the soil property, so we can just click OK for us. So as you can see that yes, now our defined material, that's a sand, appears, and it is provided with a color. Now we can drag and drop this sand item, okay, over to the model. So you can say that this is okay. So now you will find that yes, the color of the model has changed because we have assigned a new material to it. So this means that we have completed the definition of the soil stratigraphy as well as the soil properties. Now we are ready to move to the next mode, that is structure mode. Okay, fine. So we will switch over to the structures mode. As you can see that when the structures mode is pressed, we can see that this volume has become transparent. And please remember that on the left side, both your model explorer will get actually populated as it is under development. For example, if you press this volume, so in under the geometry, you can see that yes, under soil volume, we have got a generated volume 1, soil volume 1. You can just press over here and you can see that there's a material sand defined, okay, and many details are available on the left side. If there are some polygons defined, all those details and detailed definition of the boreholes all are available over here, that is in the model explorer. So now let's start defining the surface load. Please remember, in this tutorial we are not going to define the foundation through the plate elements. Instead, and though the foundations will be constructed at some depth, for this tutorial we assume that it is constructed at the surface. And what we do is that we will construct a surface that is representing the loaded area, and then we will load this surface with the deformation, which is predefined, that is a 200 mm. So let us start in this structures module. Let us start first of all defining a surface. So how can we define a surface? So you can see that here, if you press here, you will find that there's a create surface option. So you can press it over here. So you can see that it creates surface. Obviously, we know that for this tutorial, our loaded surface is a rectangle with a dimension of 1.5 by 1.5 meters. So rather than searching for all these coordinates, just to fix the 4 nodes, and we'll be able to modify the coordinates later. So just to fix the 4 nodes, 1, 2, 3, 4, you will find that all the 4 nodes have appeared over here. So now we'll be able to feed the right coordinates at this point, which will be much easier for us. So obviously at the one node will be at the origin 0, 0. And remember, we are generating this area that represents the foundation at the surface. That means for this surface, all the set coordinate will be 0. So the first coordinate will be 0, 0, and the next one will be, that means say this 1.5, 0. Then the fourth one will be, say, let me say this 1.5 by 1.5, 1.5 by 1.5, and the last one is obviously 0, 1.5. So this automatically defines a particle with of dimension 1.5 by 1.5. So now what we can do is that we can just press OK. Yes, you can find that yes, a rectangular area of dimension 1.5 by 1.5 is created at the top. If you want to see it in detail, here there are facilities known as a zoom in and zoom out. In this case, we want to just magnify the one entity, press zoom in, just select this. You will find that yes, this is the area only. Remember, we have not generated any plate. We will not be generating any plate here for this tutorial. We want to solve this problem as simple as possible. So this is the loaded area that we have created. And obviously we know that this loaded area will be subjected to a prescribed displacement. So how do you load this area with a prescribed displacement? There are many ways out. For example, here as you can see that here there's a create load, create prescribed displacement. Here there are surface displacement, line displacement, point displacement. This is one way to prescribe the surface displacement. Another way is that you can just right click on this surface. You can ask for the prescribed displacement. Here there is a create surface prescribed displacement. Just click it over here. So you will find that yes, some displacements have been imposed on it, and you can definitely go to this particular model explorer to see to add the correct value of this surface displacement. So if you see over here, you'll find that the surface displacement. Okay, this is one area which you should see. Surface displacement obviously has got three components. That's x component. So here we have kept it as a free. So as you can see that it is allowed to move in the x direction. So what you can do is that we assume that the x displacement will be restrained and the y displacement. Remember, x and y are the translations, and these two translations we will just fix it. Okay, means so that this surface will be allowed to move only in the vertical downward direction. Now look here. Here we have got the displacement in the z direction, and that is applied as prescribed displacement. Okay, and how do you specify this displacement? So you can see that if once you press it, you will find that the various conditions free, fixed, and prescribed will come. In the z direction, we have imposed a prescribed displacement. Now PLAXIS provides you the various ways of you can either apply a uniform displacement or a varying, that means a surface varying displacement, etc. So if you press, for example, the uniform here, you will find that many options, x line, increment, y line, many options are available. For this tutorial, we'll assume that we're applying a uniform displacement, and the UZ, the prescribed displacement, and this is, remember, UZ, this is the final displacement. So this displacement, let us keep it as a minus of 0.2 meters. This means that PLAXIS will apply a prescribed displacement of 0.2 meters, that is 200 millimeters over the entire area. So remember, we will solve this problem using the static approach only, and therefore accordingly we need not to bother about all the dynamic boundary conditions for this problem. So this means we have completed the definition of the surface loads. We have defined the surface that is representing the footing interface with the soil. We have imposed a displacement of minus 0.2 meters, that is in the downward direction. It is minus means it is in the downward direction on the area. Now what is left over this is that we have the soil and the structures mode completed. Now we are ready to move to the mesh. So in the mesh module also, what you can do is that you can just set it. Okay, so now look here, PLAXIS is a very simple software to use in my opinion. As far as the meshing is also concerned, we need in order to define the means that we have the automatic generation of mesh first of all, and also provides you the facilities to do the what we call as the local coarseness or the local fineness. So now let's first proceed for generating the before proceeding for the generating the mesh. Let us do one thing. Let us just zoom this area. Zoom in. Okay. Now here what I want is, we know that this is 1.5 meter by 1.5 meter loaded area is very important for us. So we need to apply a little bit what we call as an increased fineness of meshing to this area. So how we can do this is very simple. Just select this. Once you select this entity, that's a surface area, PLAXIS automatically displays the corresponding fineness factor. Now I want to increase the fineness of this particular area. So what we can do is, here we can say the refine mesh option, and here we have a coarsen mesh. So now for this case, I want to do a little bit of a refinement to this particular area. So I press this refine mesh. So you can see that. Okay, so once it is refined mesh, and press this again, so you will find that from 0.5 it has moved to 0.3536. I want to again refine it. Now it has moved to from 0.5 to 0.25. So this means that we have refined this particular area. Now we don't have any kind of a modification to be done in the model. Now we are ready to generate the mesh for this. So before that, let me just reset the zoom option. Okay, so that we will be able to visualize the full module. So just press the generate mesh button, and here regarding the element distribution, we have many options. You can set the meshing to be very coarse, medium, fine, very fine. Remember, the fine and the very fine, these are very good ways of obtaining the correct results or exact results. But unfortunately, these options will consume much of a computation time. It will increase. So for this tutorial, okay, to bridge between the accuracy as well as the time, we'll choose the medium and we'll proceed for OK. Fine. So now we'll be able to see the generated mesh also. It is, as you can see, that it is the mesh generation is in progress. So please remember that it is also possible for us to change the meshing sequence later also. So PLAXIS provides us now a facility to view the meshed elements, meshed volumes, etc. So you can press here this view mesh. PLAXIS will now take you to the, yes, as you can see that, look, this is the new window PLAXIS displays, and as I have already pointed out, we have used a refined mesh in this loaded area. As you can see that the elements are very finer at this, because this is a loaded area. We want that the mesh size to be smaller or finer at this location. And as you can see that as you move towards the outer boundaries, the element sizes increases. So this is how you can just see the full model. This is how the mesh that we have generated. So this means that we have completed the mesh as well. Now we can go straight to the staged construction, wherein we will be able to specify the various stages. So just press the staged construction mode button. So now coming to the stage construction, we need to define on the left side you will find that there is a menu known as a phase explorer, wherein we need to define the various phases. By default, when you start the stage construction, PLAXIS will define the initial phase, and in the initial phase, our intent or our objective is to calculate the stresses generated in the soil. Stresses means that we are talking about the vertical effective stresses as well as the effective horizontal stresses. So what is very important is that if you want to obtain what will be the details of this initial phase, you can just double click this initial phase, and here you will find that yes, for example, the ID, that's the initial phase, and the calculation type. And PLAXIS, in fact, has got two calculation methods to obtain the initial stresses in the soil due to sulfate. One is known as a K0 procedure, and in the K0 procedure, it automatically computes we call as the lateral stresses using the well-known Jackie's formula, that is the K0, that is the lateral stress coefficient is equal to 1 minus the sine phi, and correspondingly it obtains the lateral stresses as well. Then there is also various options like the gravity loading and the groundwater flow only. We will see this later. And so our calculation for the initial stresses, which is done in the initial phase, is very simple. So this is okay for us. So you can just press OK. So remember, every phase has its own calculation objectives. Initial phase, by its name itself, the intent is to compute the stresses at the various points in the soil deposit due to its own masses. Means it will compute the vertical stresses as well as the horizontal stresses. Now let us go for the next phase. Okay, now here important thing is when you select a particular phase, please note down what is highlighted in the model explorer. For example, in the initial phase, here you can read it. It is a model explorer very specific to the initial phase, wherein you will find that yes, the soil is activated. You will find that yes, there is a tick mark because our objective is to calculate the stresses. And remember here the surface displacement, it is untick. Okay, it is not selected because we don't want to apply any surface displacement in the initial phase. We won't apply it in the subsequent phase. So let us create another phase. So just press this button, that is add a phase. So I will call it as, for example, the phase 1. So if you want and double click it, so you will find that yes, ID, it is a phase 1, and you can we are starting the calculation starting from the initial phase. And the calculation type, remember PLAXIS has many calculation types. For example, you have the plastic, consolidation, safety, dynamic, and fully coupled flow deformation analysis. So in our present case, our purpose is to carry out the elastoplastic deformation analysis of the selected soil deposit. So accordingly, we will select the calculation type as plastic. This is one important stage. And there are many other parameters here, the deformation control parameters we will, and also one more important thing, that is the numerical control parameters we will discuss about in the next or the subsequent tutorials. So this is all regarding the definition of the parameters. That is here as far as the phase 1 is concerned, we want to carry out an elastoplastic deformation analysis. Accordingly, the calculation type will be plastic. Okay, so let us click it. Okay. Now it's also very specific that we go to the model explorer and what is being selected in this phase. Now look here. Here it is written that model explorer phase 1. And remember, our purpose is to carry out an elastoplastic analysis corresponding to an applied or a prescribed displacement, which means that in this phase 1, we need to activate the prescribed displacement. So if you go to the model explorer, here you will find that there is a surface displacement. Just activate it. Okay, so you will find that now this displacement is activated. You can just zoom it. Yes, it is activated now. So this means that in phase 1, in addition to the soil, we have applied the surface displacements also. Now just below this we will find the model conditions. Here just for the time being, I want to specify you the deformation, and here in the deformations menu we'll be able to specify the boundary conditions. And remember, as far as the model limits are concerned, model boundaries are concerned, we have used a default fixity boundary condition for the module. This will be taken up later in detail. So here what is very important is we have applied a surface displacement very specific to this phase 1, which means that we have completed all the required modes: soil, structure, mesh, and the stage reconstruction. Now before proceeding for the calculation, you would like to find out what will be the variation of the deformation of a selection point in the model. So here you will find that the PLAXIS allows you to select some as a part of the output generation. PLAXIS will also provide us some specific data regarding to the selected point in the model. So here I would like to plot a graph of the pressure versus displacement for the origin point. So now before proceeding to the calculation, select this point. So just press this button. So here you will find that yes, okay, here I want to select my point at the origin, that is 0, 0. So let us ask the program to select points which are closer to 0, 0, 0. So let's press search closest. Here you will find that yes, the program has provided us a nearest point, that is node 26. So just press this button. Here you will find that the node is assigned as point A 0, 0. So we have selected. So now in the post-processing stage, we will be able to provide or we'll be able to define the curves relevant to point A. So this is okay for us. So this means that we are now ready to proceed for the calculation. So just press the calculate button. So as you can see that yes, it is active task calculating phases. Now you can see that the details are being now hidden So if you want to show the details, you can just press the button. You will find that what are the phases. Currently the calculation is in progress. Here you can see that yes, preparing to calculate the initial phase. Okay, so this calculation may take I think that 5 to 10 minutes time, because we have some kind of a refinement, plus we have applied a displacement of the order of 200 mm. So let us wait till the analysis is in progress. So as you can see that here the PLAXIS displays the calculation progress very specific to phase 1, where we are carrying out an elastoplastic deformation analysis. And here you can see that the calculation progress is displayed to a small sketch, wherein you can see that along the x-axis we have got the deformations of the selected point, the target of which is set to say zero point 0.2 meters if you remember. And on the y-axis we have got the fz, that is the applied, that's the corresponding the vertical loads that is being generated. And the progress of the calculation you can easily okay, monitor through the simple parameter that is known as the sigma m stage, which tells you how much fraction of the applied displacement is right now applied. For example, here the sigma m stage is 0.3244. The applied displacement of a 0.32 multiplied by say 0.2 mm. So this calculation will stop when the displacement events. As you can see, the calculation is completed. We can now proceed to see the results in the post-processor module. Just press this button, view calculation results. So we'll be taken to the post-processing window. So here, first of all, in every geotechnical analysis problems, it is important that first we inspect the stress distribution in the soil profile just because of its own weight. For example, here we want to inspect the stress distribution due to phase, that is the initial phase. So what we can do is that let us inspect the stresses. So I would like to inspect the Cartesian stress, for example, sigma ZZ. Okay, so yes, here you can see that let us just zoom it to reset the view. Okay, here you can see that yes, the stress increases from 0 at the surface to say a maximum value of, you can see, the 450 kilonewton per meter square. And remember, this is nothing but the vertical stress distribution in the soil mass out of its own self weight. Now let us proceed on to the phase 1, which is very important for us, wherein we have applied a surface displacement. And as you can see, let us first see the distribution of the deformations. So we'll go to the phase displacements, use it. So here you can see that, see, this is the distribution of the displacement in the soil mass due to the applied deformation of 200 mm. So what you can do is that you can just zoom in and check the deformation. Yes, you can see that this is the contour that is a depicts how the soil deformation changes along the depth. And we can also obtain the so-called here, as you can see that this, yes, the displacement maximum value is 200 mm, which is nothing but the imposed displacement 200 mm. Now we can also obtain the stress distribution, right? So for example, if you see go to the stresses, you can go to, for example, Cartesian stresses, or you can go to, for example, yes, the sigma set. Yes, so you can say that yes, this is the distribution of the stresses within the soil mass. So we can say that here, for example, the distribution, yes, the distribution that we have. Okay, fine. Now, if you remember, we have selected one point that is a origin O, that is a point A, and we would like to obtain what will be the behavior of this node A. That means we would like to obtain a load versus displacement. So what we can do is we can go straight to the curve manager, go to the curve manager, okay, and in the curve manager, obviously, first select the point. Obviously, we have only one point here, that is a A000. Now you can go to the chart and you can press the new chart. And in the x-axis, we would like to see the force. So you can select FZ force. And in the y-axis, which is specific to the point A, we would like to find out what will be the deformations. That's our total displacement, that is UZ. And you can just press OK. So you can say that yes, this is the load versus displacement chart. So what we can do is that if you want to ensure that, okay, if you want to keep the deformation on the x-axis and the force on the y-axis, you can double click the chart and go to the chart, and you can do for example, exchange axis. Okay, so here you can see that yes, now the deformation is on the x-axis and the load is on the y-axis, and we want to have a flipping. I want to see that the displacement starts from 0 to -2. So let us do the flipping of the x and the y-axis. You can go over here, go to the chart again, right, and you can do the flip horizontal and the flip horizontal. So this is okay. So yes, so you can see that yes, now the deformation, that is the displacement of the point A, it changes from 0 to minus zero point 0.2. And accordingly, you will find that the load gradually increases from 0 to minus 500 kilonewton. Now, as you can see that this is only a curve, and here you will be able to export this. For example, if you want to retrieve this data and use it in some other application, for example, the Microsoft Excel, you can, for example, view the corresponding table also. Yes, so this table will provide you, for example, you can see that is the offset, that is the vertical load, and also the deformation used. And this vertical load offset at the origin, you can convert it to the area or the pressure, that is by dividing this load by the area. Please remember that here the associated area in the model is 1.5 by 1.5, that is 2.25 meters square. So what I did is I have copied this into Excel and constructed a curve for you. So let me just take you to the curve. So this is basically is in my, okay, fine. So you can say that yes, this is my, let me just take the preview. So from beginning, okay. So let me take you to the last sheet. Okay, fine. So look here, this is the applied load in kilonewton per meter square to the displacement. As you can see that we are not finding any kind of what we call as a flattening off, because obviously the flattening of this load displacement curve, it depends upon the type of soil. So in order to find out what would be the ultimate bearing capacity from what we call as the shear failure. So what I did is I have drawn two tangents at the two extreme points, and where they meet is taken as the ultimate bearing pressure, and this ultimate bearing capacity is obtained corresponding to this shear failure as 1500 kN per meter square. So here you can say that here I have indicated here, so that is the bearing capacity from shear failure. Okay, so ultimate bearing capacity is 1500 kN per meter square, which is the intersection point of the two tangents. Now I apply a factor of safety of 2.5, and therefore I obtain the bearing capacity from the shear failure as 1500 by 2.5, that's 600 kN per meter square. Now also, if you assume that the displacement is to be restricted to 25 mm, we can also obtain what will be the corresponding pressure to be restricted on the foundation. So from 25 mm, I have drawn a vertical line and obtained the corresponding pressure, and this corresponding limiting pressure is 750 kN per meter square. So we obtained the bearing capacity from the shear failure as 600 kN per meter square, and from the corresponding settlement criteria as 750 kN per meter square, and the lower of the two values is obtained as the design bearing pressure 600 kN per meter square. And here I want to highlight one more very important thing. In every geotechnical analysis where hand calculations are possible, please perform it so that we'll have some benchmark for comparison. For example, in this case, I did a calculation using the Tersaghi's bearing capacity formula. For example, here you will find that I have calculated the NC, NQ, and N gamma factors, and for the C values and the phi values and the depth of foundation, and I obtained the ultimate bearing capacity for this square foundation using the formula Q is equal to CNC plus QNQ plus 0.4 b gamma and gamma, and this ultimate bearing capacity is 1264 kN per meter square. And here from this analysis we obtain the corresponding ultimate bearing capacity corresponding to the shear failure as 1500 kN per meter square. So the two values are 1264 and 1500 kN per meter square, they are comparable. So this is very important in every geotechnical analysis. So that is all for this tutorial. So we will discuss about other problems in the subsequent tutorial. Till then, bye.